Hi, I'd like to give you a quick tutorial on how to use Quartus 2. So we'll start out with this truth table of a circuit that we'd like to build. So you can see we have three inputs, A, B, and C, and an output F. And F is an expression that we'd like to derive. So going from the truth table, we would order all of the combinations of inputs we could possibly have. So in this case, the easiest way to get all the combinations is to count. So in binary and 3 bits, we're counting from 0, 1, 2, 3, 4, 5, 6, 7. And I've just randomly chosen an output that we'd like, but when you build your 1-bit adder, you'll use the concept of binary addition to determine what your output should be. In this case, we only have two combinations where we want the circuit to be true. And in all other combinations, the circuit should be false or return a 0. The first combination is if A is 0, B is 1, and C is 0. And the second combination is if they're all 1. And we define the Boolean expression as a sum of products by taking any time the expression should be true and making an 3-input, in this case, AND statement for that combination. So if we have 0, 1, 0, we'll get A0, B, C0. And for the other combination that's present, for 1, 1, 1, we have A, B, C. And the reason this sum of products works is, if you remember, anything ANDed with a 1, if we have 1s ANDed with 1s, then the output is 1. And if we have anything ANDed with a 0 is 0. And if a 1 and a 0 are ORed together, then we'll have a 1. If a 0 and a 1 is ORed, then we'll have a 1. And if 0 or 0 is ORed, then we'll have a 0. So in this way, the expression will only return a true if one of the two terms present, and these would be our min terms, if one of these two min terms is present in the input, then the expression will yield a true. And for all other cases, it'll be false. The reason we picked A0, B, C0 for the combination of 0, 1, 0 was because if the combination of inputs is 0, 1, 0, then we're going to knot the zeros so that 3 1s are ANDed together, and that returns a 1. And that would only be true for that one combination. All of the other combinations would still yield a false. And the A, B, C on the same logic would yield a true only for 1, 1, 1. Okay, so that's the expression we'd like to make. A0, B, C0, A, B, C. So we're going to open Quartus. And we're going to create a new project. And we're going to want to make a folder where we're going to store all of the projects that we're going to make during the class. Just for a quick example here, I'm going to make a folder on the desktop, but you can make a folder wherever you like. And I'm going to store all the projects in that folder. And then I'm going to name this project. We want to make sure we don't use any reserved names. So avoid common names like adder and stuff like that would be reserved by the system. So in this case, I'm just going to preface everything with VA to avoid chosen names. And I'll just call it example. And I'll click next. I don't have any project files to include. We'll cover this later. This is my first project. I need to make sure that I'm using the right settings for the FPGA I have, and those can be found on the chip. So Cyclone 3 is the chip that you bought. And you'll need to double check this on your serial number, but I have the chip EP3C1 6F484C6. So that matches the serial number on my FPGA. I'm going to click next. I'm going to change this center simulation to Model Sim Altera. Everything else will leave the same. And then I'm going to click finish. And now I'm going to wait for a second. I need to create a file for this project, so I'm going to go File, New. There are many different ways for me to design my circuit. the way that we're going to learn is using block diagrams or schematic files. So I'm going to select block diagram schematic file, and that's going to open this drawing space for me. All of the gates that you've learned about, and, or, XOR, NAND, NOR, they're all present in the symbol tool here. And you can expand this folder, and then expand primitives, and then logic. And a lot of these gates are here, and the naming convention is not too difficult to understand, but if you get confused, just select one and look at the symbol and see if it's what you want. I know that I'm going to need a 3 input AND gate because both of my terms in the expression had 3 terms. Each min term had 3 terms. So I need 2 3 input AND gates and 1 2 input OR gate. Because a sum of products would start, the first level as AND gates, and the second level is 1 OR gate. So I'm going to place 2 gates here and space them out just a little bit, and then press escape to get rid of that tool. And then I'm going to look for a 2 input OR gate, and that'll be down here. There's a 2 input OR gate. I'm going to place that over here. There we go. Drag that back down to where it should be. All right, next I need to connect these gates. The best way for me to connect the gates is to use the orthogonal node tool. And that's drawing a wire. The way the orthogonal node tool works is that you can drag out and then make 1 right angle turn. And then if you need to make another right angle turn, you'll have to unclick and then click again and slide over like that. So again, I'm going to click here, and then I'm going to drag up, take 1 right turn, unclick, click again to complete that. If I make a missed connection somewhere, so I'm going to delete that, you'll get a little X, and that X is going to tell you that you've missed a connection. You need to go back and fix that. So in this case, I'm going to drag over, and if I drag too far, you can see again I have this little missed connection here. You need to be aware of those and make sure you don't have any stray wires floating around. So I'm just going to delete that, and again, there we go. That looks good. Now I need to connect my inputs and outputs. So I'm going to go back to the symbol tool, and I'm going to close the logic folder and go to the pin folder. So here I have input and output. I have 3 inputs that I need, A, B, and C. And the best organizational practice is to have your inputs actually above and to the right of your circuit, your entire circuit. And you'll see why that is in a second. It really makes the circuit look a lot nicer and easier to read. So I'm going to put my 3 inputs here, and I'm going to space them out a little bit as well. So there are my inputs. I'm not going to connect them into anything yet, but I'm going to name them A, B, and C. When naming inputs and outputs, you can't start with a number, and they can't include spaces, but all other things are okay. So I'm going to name them A, B, and C. In the expression, I have A naught and C naught, so actually I need to include a supply of the opposite of the input as well. And the way that I can do that is going back to the symbol tool, back to logic, and I'm looking for NOT, which is the inverter. So there's my NOT gate, which is an inverter, and I'm just going to place that just below A, B, and C. In this case, I only need A and C, so I'm just going to use A and C. And I'm going to use the orthogonal node tool to connect them. So I'm going to actually drag this out, and then I'm going to grab the wire tool and connect. I'm going to drag this out. Undo that. Doesn't look nice. Drag that out. Drag this out. There we go. And so now, the way I have these organized, it's easy to see that this top connection, this is my supply of inputs. The top connection is A, this is A naught, this is B, this is C, and this is C naught. So now I need to connect to my circuit. In the expression, I had A naught, B, C naught. So I'm going to connect A naught first. I'm going to come down here like this. And then B, And I'm going to try to line them up in a pattern that might be familiar to you if you've seen a circuit board before. So it was A0, B, and C0. So I'm going to leave them all close like this. And this is why we had the inputs up to the top left, because now we can keep all of our inputs organized very easily, and we don't have wires running up and down and all over the place. So the first expression is complete. Second expression was A, B, C. So I'm going to come down, leave a little bit of space just to differentiate this from the first one. A, B. So I'm going to connect to B, and C. Comes over like that, and over like that. So there we go. So we can see really easily that I've got these three connected to the first AND gate, which is my first min term. These three are connected to the second AND gate, which is my second min term. If I have an error and I need to double check to see something is working or not, I can double click on a wire and see everything that's connected to that wire. So I can see that this is A0, this is B, and actually both AND gates are connected to B, which they should be. And this is C0. This is connected to A, B, and C. So there I've double checked all my inputs and that's wired correctly. I need an output now. And so I'm going to go back to pin, output, drag that over there. That's my output. It's connected properly. It should have a little wire connecting it like that. And I'm going to name that F. Okay, so the design is done. We've got the schematic done, so we're going to save the schematic. We're going to make sure that we save it in our folder. So we're going to make a new folder here, project folder for the example. So we're going to have VA example. Make sure we save all our files into that folder. And then let's see. So now we need to compile. This is the button up here to compile. This will tell us if we've made any critical errors. If it returns any warnings, you can typically ignore those. They're usually warnings about the circuit not being connected to pins yet, which is not something we're concerned about right now. All right, so we have full compilation, 9 warnings, and yeah, those warnings are about pin assignments, which we haven't done yet, and so that's not a big deal. You can sort of ignore this statistical output. It's not useful for us at the moment. Next thing we need to do is to generate a simulation netlist, which will allow us to run our simulator. So what we're going to do is we're going to come over here to processing, generate functional simulation netlist. That's going to allow us to run a functional simulation which does not take into account the physical delay of signals propagating through the circuit. So we just want to see, does this circuit do what we want? And we're not worried about how long it takes to do that. For combinational circuits like that, that's a common analysis technique. So the next thing we need to do is actually get ready to simulate the circuit. So we're going to go to File, New, and we're going to make a vector waveform file, which is going to tell the simulator what inputs to put into our circuit. It's going to bring up a new window. We can switch back to old windows in these tabs up here. We need to complete our vector waveform file, so we're going to double click in this column here. We're going to make sure that our radix is in binary. We're going to click the node finder, make sure that our filter is set to pins all. Then we're going to click list. All of our pins should show up, and we're going to select all of the pins. A, B, C are our inputs, and F is our output. And then we're going to click OK. It's going to list all of them. You want your leftmost bit to show up at the top of the list, and your rightmost bit to show up at the bottom of the list. So that's how we have our inputs set up right now. That's good. And we're going to group these inputs as our inputs. And there's going to be a break in the video, so please continue to this second video.